Okay? All right, so today I'm just looking at these last three models. I want to look at a quick example of each one and how to use it, okay? And just kind of review what we talked about Friday a little bit with each ones, and then work on application, okay? So the Gaussian model, what did this one look like? That was our bell curve, okay? The Gaussian model is our bell curve that we saw with our normal distribution, okay? What's the key part of the equation here that tells us this is a Gaussian model?
The squared in the exponent.
Yeah, x is squared in the exponent, okay? You have an x squared in the exponent.
Exponentception.
All right? So, I want you to know the term Gaussian. I want you to know that it looks like a bell curve. And I want you to know that if you see an equation where e has an x squared power, that's going to match up with the Gaussian model.
Wait, isn't this day 8?
Day 9.
No, this is day 9.
It's not.
We said the same first slide.
Why is this day 8?
It's the same beginning.
All right, now logistic. What does the logistic model look like?
Is it like the sideways one? It looks like the S.
Okay, yeah, it kind of looks like an S on its side. You know, it's increasing
And then like levels out.
and then levels off. Good. The one thing to remember here, and we'll see this clearer later when we look at the application, it actually has a horizontal asymptote on the top and the bottom. It's not like the logarithmic function. Remember the logarithmic function, we learned the parent for this. Looks like this, and it continues to increase. Its range was all real numbers. The logistic growth model, its range goes from whatever that bottom asymptote is, typically 0, up to whatever that top asymptote is, okay, which is usually capacity. Like if we're talking about a virus spreading, it's the total number of people in the area. So that's going to be the cap as to how many we could have. All right. Now, the key part in this is that you have this binomial in your denominator that includes the exponential portion of the model. All right. So we have an e to the x power in the denominator of the fraction. Okay, that's going to be the key thing that you look for when you're looking at, is this a logistic model? Okay? Does that make sense?
What was the key thing? What did you say?
That binomial part in the denominator. You have the exponential part in the denominator. Okay? So let's look at a couple of examples here real quick. First of all, the bell curve.
Wait,
All right?
Can I just ask a question about the logistic growth model quickly?
What?
Can it be crossing the x-axis?
If the entire thing were shifted up or down, yes.
So it could
Like-
go negative.
Where would it be?
Potentially, if you had like a minus 10 or something, okay? Like if we were talking about filling up, like something at sea level.
Below sea level.
I don't know, if it was starting below sea level and then we were getting up above sea level, I guess theoretically you could have something like that. Okay. Most of ours aren't really going to be like that though. But that's a good question. Take a look at the Gaussian model. Here's an example. Notice that when you just have x squared, it's not x minus anything. Notice where the peak is. The peak is right on the y-axis. Okay, so your y-intercept actually will be where that maximum point is. All right? Now, we said this was a bell curve. Where or what was the peak on the bell curve in relation to our normal distribution?
It was like where the most is, like the large percentage.
Okay, it was where the median and the mean and the mode were. Okay? So, and particularly here we look at the mean, all right? Now, I say that because our example right here shows us a Gaussian model for SAT scores, okay? In 2005, we created a model here for SAT scores, okay, where X is the SAT score, okay? Now notice, we said the peak of our model on the normal distribution is the mean, right? Think about our function transformations. I know we didn't learn the Gaussian parent function, but that's okay. Where is our mean shifted to in this case?
It would be 520.
520. If it's not shifted at all, our bell curve has a peak on the y-axis when x is 0, right? Notice here, we have x minus 520. All right? That's going to shift our whole thing to the right 520 units. Which means, what was the average score for all of our SAT scores in 2005?
520.
It was 520. Okay? That was the mean for all SAT students in 2005. Whoop.
That's not that good.
For like one section, probably.
That was for math.
Alright.
Yeah, it says SAT math scores. Sorry.
It's
Not composite.
All we care about is math.
Okay? Does that make sense?
So it shifted it 5 to the right?
Yeah, it shifted it 520 to the right. So instead of being right on the y-axis, it's now shifted 520 units to the right. So we
But what
know where the mean was. Yes.
are we doing? Like, are we solving for something, or do we just like make a statement?
Really, this one we just made a statement, okay? Now, one thing to understand, if you were to graph this, okay? If you were to punch this into your calculator to graph it, be careful punching it in, and one thing I will say is you want to make sure that you put parentheses around the entire exponent. Otherwise, it will only raise it to that negative x minus 520 squared power, and then it's going to divide the entire thing by that 26,450. So put parentheses in your exponent. The other thing is, these ones are hard to fit in your window. Okay? The x shouldn't be hard because it says do x from 200 to 800. Alright? But the y is hard because actually the max here is at 0.0035. So you're going to be messing around with the y and trying to find it when the highest this thing actually goes is 35 10,000ths. Okay? So this is where if you hit on your calculator, if you hit zoom and scroll down to choice 0, it's zoom fit. And it will actually fit it in the window.
So it'll do it for
It doesn't do a great job on all functions, but on the bell curves it gets it really good. Okay, it'll fit it right in the window for you. Yeah, Katie?
So does that make our mean 520?
Yes, the mean score was 520.
Why was it?
I'm confused at how you got
Because
that.
it's like a distribution.
Oh, I get it, but
The
like,
one
why
that
did they
comes
know
from
to put the
the
520 in the equation already?
Well, they had already calculated what the mean was. They were we would already know the mean and we would construct the bell curve from it. Just like when you guys were sketching these, you started with the mean and you put that mean at the top, and then you did, -1 standard deviation and +1 standard deviation. You remember doing that?
Yeah.
Okay? And you figured it out that way. Here, we actually have a model that does it more accurately rather than using the standard deviation. Okay? All right, so that's just one application. All right? A second application is our logistic growth. Okay? This is also known as the sigmoidal curve. Kind of a cool word to say, sigmoidal. All right? Now, you'll notice here again, I give you an example here. Notice that in the denominator, we have this exponential part of it. E to the negative 5x is in the denominator, so it's 1 plus e to the negative 5. That's the part of this function that tells us this is logistic, okay? When you see that, it's going to be logistic, okay? The model on the right there is kind of nice because it shows us how initially our growth rate is speeding up. It's gaining faster and faster and faster, but this is kind of the turning point right here. In calculus, we would call it a point of inflection, okay? But now, it may still be increasing, but it's increasing at a slower rate. It's kind of slowing down, all right? So here we're speeding up. At this moment, we stop accelerating and we start to slow down a little bit, even though we're still going up, okay? So let's look at the example here, looking at the spread of a virus, all right? Here's a college campus. You guys are going to college next year, and when you come back from break, or some of you, wait, are any of you guys seniors?
Oh, no.
Oh, I don't have any seniors. I have seniors in both of my, oh wait, you're a senior, that's right. I thought I had at least one in every section. You guys are going to college pretty soon, all right? Let's say we have a campus of 5,000 students and one person comes back sick, all right? And for some reason nobody takes any medicine or pays any attention to what's going on. So this virus just spreads rampantly across campus, okay? Now, one thing that's kind of interesting is that every institution has a certain percentage that if a certain percentage are sick, they just cancel classes to let everyone stay home and stop infecting each other and get better, hopefully. Okay? So this college has a 40% rate. If 40% of the students are sick, they'll cancel classes. So
Do we have that at high school?
we have a number. I don't know if it's 20% or what it is, but still a lot. It would take a lot to cancel class for illness.
Entire high school or 20% like a grade?
I don't know. But
So that's like 100 kids.
40% of 5,000 is how many kids?
Wait, what?
A lot.
Oh, come on. 40% of 5,000 is how many?
2,000.
2,000. Thank you. All right?
Let's plug it in.
Come on. 2,000 students. Okay? Now, we could use this model. Again, you see this 1 plus something e to the t power. That's what's telling us this is a logistical growth model. Okay? How would I figure out how many students are infected after 5 days?
So you just plug in 5.
Plug in 5 for t. Okay? We're not going to bother doing that because it's so simple. You just plug it in your calculator, you figure out how many there are. Okay? The second part is a little bit more challenging. So we actually have to solve the equation. All right? After how many days will the college cancel classes? All right? So how are we going to figure that out? Keep plugging in different values of t and hope it's not like 100 days.
So we know that our limit is 2,000 kids, right?
Yeah?
Plug in.
So would we do plug in 2000 for y.
Yes, there we go. That's a little more efficient. All right, 2,000 plugged in for y equals 5,000 over 1 plus 49.99 e to the negative 0.8 t. Okay? Now, by the way here, just, you don't have to know this, but I figure I just point it out here. How many students did we have? 5,000. So that's theoretically the maximum number who could be sick, right? Guess where our horizontal asymptote is? 5,000. Where'd the 5,000 end up in our model? In the numerator.
Well,
That
technically it's in the denominator.
that numerator here
Oh no.
is gonna be that top asymptote. So if you're trying to plug this into a calculator for your y window, look at that numerator and that'll help you determine what you will need to set your window at. Okay?
Is this just for logistics models?
Yeah, for
The
logistic.
bottom is usually going to be 0 unless it's affected like by upper, unless it's translated.
Yeah. And by the way too, you could also use Zoom Fit for this and it'll probably give you a pretty good window too. So. Alright, so now we do need to solve for t, okay, to figure out what time will give us 2,000. Alright, so let's do this algebraically, and I actually want to show you a little tip for solving these, okay? So check this out, alright, we've got 5,000 over that. So what I'm going to do first is I'm going to multiply by a 1 over 5,000. This is going to make my numerator 1, right? That's the same thing as dividing by 5,000. Okay? So I have now 2/5 equals 1 over 1 plus 49.99 e to the negative 0.8 t. Okay?
Why do you have? Oh, can't you just make it 5 over 2?
And then what?
Flip the other side.
Yes. That's the thing that'll actually make this a little bit easier to solve. If you keep this in mind, we have 1 over that mess on the bottom. So since it's 1 over, if I just flip it, I have now 1 plus 49.99 e to the negative 0.8 t equals 5 over 2. Take the reciprocal of both sides of the equation, and now our algebra is a little simpler, okay?
Could you add that 1 in the 49.99 and make it 5,000?
You guys tell me,
No. Nope.
why not?
Because it's being multiplied by the.
Okay.
Yeah, this is being multiplied by the e. It's just like a 1 plus 49.99x.
Oh,
You
okay.
can't combine those.
Because
So,
there's like order
we
of
have to
operations.
divide by the 1,
No, you can just subtract it.
or subtract the 1, sorry.
Yep, subtract the 1, so now we have 3 halves.
Wait, what was it that you were saying?
You can't do 1
You
plus
can't. 1 plus.
4,999.
Oh.
Okay,
And then you do natural.
Divided by.
Yeah, then you divide by.
divide by 49.99. So what's 3 halves divided by 49.99?
Would be 499
It's 0.00030006.
Alright, so that equals e to the negative 0.8 t power.
You just
Okay.
take the
Take the
natural
natural
log
log.
of the other side.
There we go. Take the ln of both sides. That cancels out the exponential. So we have a negative 0.8 t equals what?
Oh, whatever that big number
That
is.
number divided by negative 0.8.
And that is negative 8.11.
Negative 8.11 and
Plus two
change.
ones, five.
Okay. So we leave that in the calculator because we're not going to round until we get to the very end. And we divide by negative 0.8. And what do you get t equal to?
Divided by negative 0.2, and you get 10.13.
Okay. 10.13.
Makes sense.
Okay. Is everyone with me?
Yeah.
All right. So if nobody takes any medicine and everyone is coughing all over everyone and being inconsiderate, this whole place is going to be shut down in 10 days. All right.
But if the sickness lasts for longer than that period, like if it's only a 2-day sickness, you can get over it quick and then come back to school. So you won't ever reach that 40%.
Well, and again, yeah, that's theoretically, when you're developing this model, you would assume you would have to take all that into account. That's why they make what are called SIR models. What is it? I forget what the S is, but it's something infected recovered models. And it takes into account the fact that, certain people are susceptible. That's what it is. Susceptible to the disease. Some are infected. Some are recovering. And then it also assumes that if you just had it, you're not going to catch it a second time, which may or may not be accurate. So the SIR models, that's like a whole thing. Kind of an interesting idea, but all right, so at some point, maybe the 11th day of this thing going through campus. Oh wow, that's real small. All right, so somewhere around the 11th day, day 11 will be canceled.
So you'd have to round up?
Yeah, 'cause it's a little bit
Just
faster than
communicate.
it is,
If you just communicate day 11 or the 10th or 11th day, if you just communicate your idea there, it'll be all right. Okay? Does that make sense? Okay, so that's just one other example here. Really the most challenging part here is just the algebra, getting that right. Okay? One more here with the logarithmic, okay? You guys know what the logarithmic looks like, even though I just showed it there for you. Here we have a 1 plus the logarithm, just showing that we can translate this up or down however we want, okay? But let's look at magnitudes of earthquakes. These are kind of cool. The Richter scale. The magnitude of an earthquake of intensity I is given by the log base 10 of I over I sub 0. I sub 0 equals 1 is the minimum intensity used for comparison, okay? It's measured of the wave energy of an earthquake. So they have those seismographs that measure the intensity. And that I sub naught would be like the normal rumblings underground that when there is no earthquake at all. Okay, there's always certain vibrations and things under the ground. So that's kind of our baseline. But it says here, 2001, the coast of Peru experienced an earthquake that measured 8.4 on the Richter scale. In 2003, Colima, Mexico experienced an earthquake that measured 7.6 on the Richter scale. Find the intensity of each earthquake and compare the intensities. So notice here there's a difference of 0.8 on the Richter scale. Okay? Let's look at the intensities though. We have here 8.4 is going to equal the log base 10 of I over I sub naught. And I'll put I sub P for Peru there, just so we can distinguish these, okay? And a second equation, we have 7.6 equals the log base 10 but I'll put I sub m for Mexico over I sub 0. Okay? Now, how would I compare these? I've got to do what with the logarithmic equation? Let's say I want to solve it for I sub p, right? So how would I solve this for I sub p?
Does it tell you that I zero
Put
is
in
one?
divide by the, oh, you raise it to the power of 10, which is base 10.
Would you put exponential?
To get rid of the log.
Okay, we got to get rid of the log by rewriting this. 10 to the 8.4 equals I sub p, and they say I sub not equal, we could let I sub not equal 1. Okay, they said that right up here.
Okay.
Okay, so we're going to say that's I sub p is 10 to the 8.4. Here, it'd be 10 to the 7.6 power equals I sub m. Alright?
Okay.
So, even though on the Richter scale it was only a 0.8 difference, it's actually a difference of 10 to the 0.8 power in intensity. So every unit on the Richter scale is actually 10 times stronger than the previous one. Okay? Alright, we'll let you guys go. Have a great day.